Many machine vision applications require only a few elements, using just a camera and some software to function. Other systems need to interface to peripheral devices to control motion, report results, or interact in some other way. On-camera digital I/O lines can be used in some cases to communicate binary results, such as a simple pass-fail output, controlling a reject gate. But if more complex messaging is required, this can mean extra hardware has to be integrated, adding more cables and the use of additional software. My name is Rob Webb and I am the Sales Enablement Manager at IDS. And in this video, I will be talking about alternative ways to communicate with peripheral devices directly via IDS cameras, namely the I2C or I2C and UART interfaces, offering the opportunity to reduce hardware costs and system complexity. I will cover the technical details of the UART and I2C interfaces, discuss different use cases, and finally I'll demonstrate how these interfaces can be used on our UI Plus cameras and with our IDS Peak software, along with a demonstration. There are a few general concepts to consider when talking about communication protocols. Firstly, the interfaces I'm talking about in this video are both serial communications. In simple terms, this means that rather than having separate wires for each bit of data, known as parallel communication, we have a single wire and transmit each bit one after the other. This has the advantage that the cabling is simpler and cheaper, and although there is an inherent latency because we can only send one bit at a time, it is rarely an issue, and any devices that use serial communication will do so because it is well proven that this data transmission method is perfectly adequate. UART and I2C being serial interfaces also means that it is viable to use these interfaces on compact industrial cameras. So, what are the key differences between UART and I2C? UART, Universal Asynchronous Receiver-Transmitter, is what is known as a two-wire bus and is designed for point-to-point connections, meaning you can only connect and control a single device. The connection uses a transmit line, TX, and a receive line, RX, for communication, and with this connection you can have a full duplex communication where both the camera and the peripheral device can talk to each other simultaneously, or half duplex, where the camera and the peripheral device take it in turns to communicate. If you use just a single connection, this is a simplex interface where only one device is transmitting data, and this is also supported. If the device uses the same signal levels or logic levels as the camera, in this case 3.3 volts, it is possible to connect the device directly to the camera. And this keeps the complexity low but limits the cable length to around 30 to 50 centimeters. If, however, the device requires RS-232 or RS-485 signal levels, an additional but low-cost level shifter component is required. This has the benefit of longer cable lengths, up to 20 meters with RS-232 and up to 1.2 kilometers on RS-485 between the camera and the device, and also offers more electrical protection and noise tolerance. I2C is also a two-wire bus, however it is half duplex only. Either the camera can transmit or the device can transmit. This is because the second wire used is a clock signal, used for timing. So we have a data line, SDA, and a clock line, SCL. I2C is designed for intra-board communication, so only supports short distances, typically less than 1 meter. But for most applications, this is normally sufficient. The main advantage of I2C is that multiple devices are supported. This is achieved through addressing. We would send a message to control a specific device preceded by the address, so the specific device knows that a message is intended for it. All other devices connected would simply ignore the message. I2C does not require any intermediate level adjustments and is designed for connecting devices on a network. So looking at the table, we can see the main differences between UART and I2C. Both are two-wire buses, but UART is an asynchronous interface using control bits to communicate, and I2C is synchronous using a shared clock signal. UART is a one-to-one or point-to-point interface, limiting the number of peripherals to one per channel, and I2C allows multiple devices via the addressing system, something UART doesn't use or require. And you might say that because UART is point-to-point, it is a simple interface, and as I2C supports multiple devices, the complexity can be seen as higher, but needn't be if you only have a single device connected. We can also add the speeds of up to 1 megabit per second on UART and 3.4 megabits per second on I2C, and this may have some bearing on which interface to use. Turning now to which peripheral devices we might interface to our UI Plus cameras via I2C or UART. I2C is a typical interface for writing to local EEPROM memory for storing information of a system in an embedded environment. Any number of sensors such as thermometers, light meters, pressure sensors and similar might be used in a system to provide feedback about the environment. Again, with embedded systems, small display devices or HMIs can be interfaced directly to the camera to transmit information to the display. And in systems that require more than the limited number of I/O lines available on a typical machine vision camera, these can be extended with I/O expansion boards. For devices using UART as an interface, there is some overlap with I2C, for example, sensors providing environmental feedback. But also we see UART used with debug tools, converting between RS-232 and USB, in wireless transmissions such as Bluetooth in cases where we need a remote connection, and GPS receivers for applications where we need location information, and other control devices such as lighting controllers and lens controllers. You can see from the list there are many potential partner devices that would work alongside a camera in a system. Some of these devices may be operating independently from the vision side of things, and others may interact directly, such as controlling focus on a lens, switching different lights on and off, or adjusting intensity or wavelength of lighting, or transmitting results to reject or sorting mechanisms. Next, let's take a look at which IDS cameras you can use for these interfaces and how the configuration is achieved. First, looking at UART, this is supported by our XCP, XLE and XLS USB 3 cameras from revision 1.2 onwards. The XLE and XLS offer board-level options ideal for cost-sensitive and space-limited embedded and OEM solutions, and XCP is our small house industrial camera. Available with the latest sensors from onsemi and Sony, including the Sony StarViz 2 series with excellent near-infrared response and the new IMX900 sensor also offering excellent near-infrared response as well as low-noise imaging. To configure the UART interface, we can either do this programmatically or we can set this up with IDS UI Cockpit. On the hardware side, we are using the general purpose lines GPIO1 and GPIO2. In the generic parameters dialog, we need to set the line selector to line 2, as this corresponds to GPIO1, and then set the line modes to output and the line source to UART-TX. This is our transmit line. Then, under the UART control section, also in the generic parameters dialog, we set the UART RX source to line 3 to correspond to GPIO2, and this is our receive line. We will see the actual transmission of data during the demonstration. The I2C interface is offered on our board-level USB 3 LE and LE-AF cameras, the LE-AF offering liquid lens control for active or autofocus. And we also have the ACP cameras, our semi-custom camera option with USB 3 and GigE interface, and remote head and interface options via flex cables, offering larger format sensors from Sony. All of these are also ideal for OEM solutions and include more on-camera features, especially the ACP, which has features such as auto control, color correction, lookup tables, line scan mode, chunk data, sequencer modes, and wider trigger controls. As the I2C lines are already designated in our cameras, there's no hardware configuration to be concerned with. In an IDS Peak cockpit, there is a dialog for the communication setup where we can set the address and register into which we are communicating, as well as advanced settings covering the byte ordering, communication speed, and acknowledgement polling, and a section also for entering the data we want to transmit. We can now look at an example using an XCP camera with the UART interface to control a servo which is driving a conveyor belt. And for this, I have my camera, a USB 3 cable for the data transmission, and an I/O cable for the UART interfacing. The servo uses RS-232 levels, so I'm using a widely available level shifter to convert from 3.3 volts to RS-232 levels. If the servo was also working on 3.3 volt signaling, it would also be possible to connect the camera directly to the servo. I have here a camera mounted above the conveyor with 3 objects mounted, and we can see the live feed from the camera showing one of the objects. The conveyor position is driven by this servo, where we can set the conveyor speed, direction and position. From IDS Peak Cockpit, I can set the parameter UART TX data length and then enter the data I wish to send to the servo. I can then click on send and the servo moves the conveyor to the new position. And if I enter another value, we can move the conveyor to the 3rd position. We can also query the servo status, for example, and in this case we set the UART RX status to listening by clicking the UART RX execute button, and then send the query to the conveyor, and we see the result in our UART RX buffer. It is a simple demonstration, but we can imagine this connection also to a lighting controller that could control lighting intensity or switch different styles of lights on and off to highlight different features or defects on an object, or to control a stepper motor on a zoom lens for different magnification for a microscopy application. And the numerous peripheral devices we saw earlier can be controlled via an IDS camera. It is simply the case of identifying the right camera, providing the right performance and interface. One final point, we also have a very active customization division. So if you need something non-standard for your application, then please make contact with your local sales representative to explore the possibilities. We have a video available here on our Vision channel that covers this topic in more detail, and it is well worth a watch. To summarize, the UART and I2C interfaces are a powerful but simple addition to IDS cameras, and using these can simplify your system both with respect to hardware and software, saving time and money for your development. I hope you found this video informative. If you have any questions, please do contact us. And for now, thank you for your time.